And so, hold on here. Okay, so today we're going to talk about explore some more properties of time series. We started that a little bit on Tuesday. And then we're going to talk a little bit about some kind of introductory time series functions that, as it turns out, we're not going to use a lot in this class, but as you read time series related literature or scientific papers that have used time series analysis, you may very well see those operators and functions. So I think it's important that you're at least familiar with them. And we'll see them again next Tuesday when we talk about some ARMA models for time series. Okay, so today our topics are, we're going to talk about these sort of characteristics of time series. And some of these characteristics are not necessarily unique to time series, but they apply to time series nonetheless. So those are things like expectation, mean, variance, covariance, correlation, stationarity, autocovariance, autocorrelation, correlograms. And then we'll talk a little bit about some really simple time series models, which we saw just briefly the other day, white noise and random walk. And then we'll end by talking about these backshift and difference operators, which are important in sort of the analysis of time series from a more theoretical standpoint, but it allows you, you'll see some tricks next Tuesday where they can actually be really useful for you. Okay, so the expectation of any variable is its mean value in the population. So when we talk about expectation, we're really thinking about the mean. And oftentimes you'll see this abbreviated with this capital E. So E of X would be the expectation of X. That's just defined to be the mean. And oftentimes you see that with a mu, a Greek letter mu. And as most of you are probably really quite well aware, you can estimate the population mean, mu, from a sample by just summing up all of those values and dividing by the sample size, right? That's really pretty straightforward. Everybody's probably done this many hundreds of times. The variance now is the expected deviation of X about that population mean. So it's the difference between any observation and its mean squared. So the expected difference squared. And we usually refer to that as the variance. And oftentimes you'll see that abbreviated as sigma squared. As we move on in this course, we'll actually move away from a lot of the Greek characters and use pretty much only Roman characters and get rid of the squared aspect too with respect to variance. But anyway, we can estimate the population variance from a sample by going through the sample size. So starting at 1 up to n numbers, and you just take the difference between that value and the mean that you just calculated from the previous slide, square those, sum them all up, and then divide by 1 over n minus 1. And the reason we typically do this n minus 1 is because we've lost a degree of freedom when estimating the mean. So that's why sometimes you'll see this as 1 over n, but typically it should be 1 over n minus 1. Okay, so given a mean and a variance, now we can talk about two different variables. Let's call them x and y, and we can generalize that variance statement. So here, just back up 1 second. Remember we had x minus the mean squared. So that's just x minus the mean times x minus the mean, right? So this is the statement for variance into covariance. So now we're thinking about the relationship between x and y. And this is the expected value of x minus the mean of x times y minus the mean of y. And you can estimate that from a sample just the way you would with a variance. So you just take the x minus the mean of x, the y's minus the mean of y's, sum all those up and divide by 1 over the sample size minus 1. Okay, so let's talk a little bit about covariance, because this is a really important concept in statistics in general, but certainly in time series analysis. So here I have two variables. Here's x and here's y. And we want to know if there's some covariance among the, well, there should be some covariance among them in this case, but we want to try to figure out what that is. So if we cut this space up into 4 quadrats, defined by, here's the mean of X, that's this vertical line here, and here's the mean of Y, this horizontal line here. So we know anything to the left of this line, X minus the mean is going to be less than 0, and anything to the right of the line says X minus the mean is going to be greater than 0, right? This value minus that mean is definitely positive. Similarly, with respect to the Y, anything above here, the difference is going to be greater than 0, and below this line, the difference is going to be less than 0. Okay. So now, if you think about all of these, this is a case where these are positives, right? These are all positive. These are negative, and these are negative. So if we summed all of these up, there would be a lot more positives than there would be negatives, and we would have positive covariance between these two. And just looking at those, many of you would have just guessed that those two were covariant, right? There does appear to be actually some sort of positive relationship here. So that's really all a covariance calculation amounts to. Is just cut up your space, add up the number of positive relationships, add up the number of negatives, and wherever that net sum falls, you either have positive covariance or negative covariance. Okay, so once we know something about covariance, we can talk now about correlation. And correlation is really just a dimensionless measure of that linear association between two variables, X and Y. And the definition of correlation is just the covariance standardized by the standard deviations of X and Y. So the correlation, we often write that with a rho or small r, you'll see in the future, is that covariance divided by the standard deviation of X and the standard deviation of Y. And the nice thing now is this is dimensionless. There are no units here. So if X was temperature and Y was fish length, the covariance would have this funny units to it. But once we divided by the units for temperature and the units for length, it's dimensionless, and it's bounded by -1 and 1. So correlation always scales between -1 and 1. And in fact, I can see there's a typo on here because this should be less than or equal to -1. Correlation can be -1 and it can be 1. So these should be less than or equal to, less than or equal to. And of course, you can estimate rho from a sample by computing the covariance, estimating the standard deviation of X, the standard deviation of Y, and you get the correlation between them. Okay, so now given we know something about variance and means and covariance and correlations, let's talk about stationarity. So let's think about a single value X of t. The expectation for X at t is taken across an ensemble of all possible time series. Remember on Tuesday, we had this plot where I had all these realizations of a white noise process, but we only were able to sample one of them. So now we have, at any point in time, right, we just have one value, X of t. So here's an example right here, right? Whole bunch of white noise series. The mean is 0 here. And our single estimate or single realization, sorry, of that process is our estimate of the expectation. So here at time 1, there's the expectation, there's the expectation, there's the expectation, etc. Right? So we're not actually going averaging all of these because in the population, it would be 0. But we don't know all of those other ones. So we're stuck with one realization. And so that here, in fact, our mean is actually changing a little bit from time to time. If that expectation for X of t is constant across time, we say the time series is stationary in the mean. And if you just step back for a minute and think about what does stationary mean to you, well, it pretty much means immobile. It's not moving. So the idea is that it's this mean, the expectation is not varying. So if we go back here, certainly in this case, that's not varying at all. And here you're saying, well, yeah, it's varying, but the real question is this really different than that, different than that, different than that, different than that, in a systematic sense? Because if we were able to resample these processes over and over and over and over again, we'd end up with something like this. So in this case, the mean of these is actually fairly stationary. Okay, so what's nice, why do we even care about this? Well, one of the nice things is that it allows us to describe some statistical properties about time series. So in general, we talk about stationary time series if there's no change in the mean or the variance, there's no systematic trend, and there's no periodicity to it. So if you can eliminate all of those bits, there's no systematic trend one way or the other. It doesn't start here and then go in big conical shape because the mean and variance, you're doing that. If you can eliminate all of those cases, then you can probably assume they're stationary. Okay, so given that, now our definition of stationary says no change in the expectation, no change in the variance, no trends, and no seasonality. So here's a little quiz for everyone. Go ahead and type into the chat, which of these do you think are stationary? I simulated these, so I know the answer. Okay, we got some guesses going in. D, yeah, that's looking pretty good. A, D, all. A, B, D, maybe all. Okay, that looks like about all of you. The correct answer is every single one of them. All of the above. So it's a little bit tricky in this case because I've only simulated 100 time points. And if this were, 10,000, it would probably look a lot more stationary. But what this means is that our eyes are really bad at identifying stationarity. So we really need some tools to help us do this, right? I mean, this is kind of a classic pitfall in statistics where people are like, oh yeah, I just eyeballed it, it's good. I mean, that's the engineer's approach, right? Who needs statistics? The relationship is strong. Okay, so to do so, we're gonna look at a couple of functions that we'll use a lot of in this class actually moving forward. So for stationary time series, we can define what's called an autocovariance function. We typically describe this as gamma sub k as something that looks like the variance or the covariance. But here now we've got x of t minus the mean times x at t plus some lag. So honestly, this could be minus. It's typically just written plus, but you can imagine we've got two time series, and now we're going to shift them one or more units apart, and then we'll compare the rows after they've been shifted. So that's all autocovariance is. We take a time series, we replicate it, we move it a little bit, and then we compare the rows. So that if k, the lag here, is 0, and this is x at t minus mu times x at t minus mu, and we said earlier that's just the variance. So the autocovariance at lag 0 is the variance, because here we haven't shifted them. We've taken a time series, we've replicated it, and now we're just comparing the two. Okay, smooth time series tend to have large autocovariance functions for large k. So we could go out to lag 1, 2, 3, 4, 5, etc. Those are going to have high autocovariance as we start to shift these things a long ways away from each other. In contrast, so-called like choppy time series have an autocovariance function near 0 for small k. So that means we take this, we replicate it, we move it here, there might be some autocovariance, and then pretty soon there's none. It's just 0 as we go away. And we can estimate this autocovariance function from a sample just as we would variance or covariance between those. So you would go from 1 up to n minus whatever the lag is here, right? Because when we've replicated these and shift them, we're losing values off the ends of the time series. So you can't go all the way to n. And you would just take x of t minus the mean times x at t plus k, again, could be minus depending on how you're thinking about this, minus the mean, sum them all up. And here it's 1 over n. And this is, we'll talk about this some other time over a beer. Let's put it that way. This is a debate that's brewed in statistics for a long time. And I should point out that in general, if n is really large here, it doesn't matter if this is n or n minus 1. And by large, you don't have to get very large at all. Like 30 would be enough that it hardly makes a difference. Okay, so we have an autocovariance function. Based on that, now we can define an autocorrelation function. Just like we moved from covariance to correlation, we can move from autocovariance to autocorrelation. And the autocorrelation function, or ACF, you will often see this written, is just that autocovariance function normalized by the variance. So here we're going to call this rho, and now we're going to give it a subscript k, which refers to the lag. And the autocorrelation function at lag k is the autocovariance at k divided by the variance. And we know that the autocovariance at lag 0 is equal to the variance, so these two are equivalent. And importantly, you can think of that this ACF, the autocorrelation function, measures the correlation of a time series against a time-shifted version of itself. Right? So you have a vector of a time series, you just replicate it, and now you shift it one way or the other, and you ask, what does that correlation look like? And again, you can estimate this from a sample. You compute what the ACVF is, divide it by that at lag 0, and you get this autocorrelation function, which is a lot like the correlation, but now we're talking with respect to some lag k. The ACF has some important properties similar to correlation. Here I got the signs right, so it's bounded by -1 and 1. The autocorrelation at lag k equals the autocorrelation at -k. So it doesn't matter if you shift these things one way or the other, you're going to get the same result. And the autocorrelation function of a periodic function is itself periodic. And we'll see some graphical examples of this to help you kind of visualize this in a minute. So if you've got some time series that has some real strong seasonal aspect to it, if you look at the autocorrelation function, it's also going to have some sort of seasonal wiggle to it. And the autocorrelation for the sum of two independent variables is the sum of the autocorrelation for each of them. So if you had x and y and they were not at all related to each other, Eric wants in. If you computed the autocorrelation for this one and the autocorrelation for this one and added those, it'd be the same as if we took these, added them up, and then computed the autocorrelation function. Okay. So the way we typically visualize autocorrelation is through what's called a correlogram. And the correlogram has some important things that you should see. So we know that this ACF is bounded between -1 and 1. So typically you'll see a plot looks like this. It should always be scaled here. And then we usually draw a line at 0 to just demark this. And then we have various lags that we're going to explore. And most softwares, all of them that I'm aware of, by default just show you what it is for positive lags, because remember, it's symmetrical. So there's no real need to look at the negative lags here. And some of the important things is we know that at lag 0, the autocorrelation function has to be 1. Because now we've got a time series, we've replicated, we haven't shifted it at all. So the correlation of something with itself is in fact 1. And it's kind of weird, but like ours and a lot of softwares show you this all the time, which is a bit strange because we all know that this should be 1. So I don't understand why they do it. Well, in general, people usually, the conventional wisdom is that this is here just as sort of a scale bar. So that when you're looking at the autocorrelation function at these other lags, it's really easy to just look at this. As though you couldn't just read the scale on the left anyway. Anyhow, that's the way it is. And then what you'll typically see are some lines, some horizontal lines here that are indicating the approximate 95% confidence interval. So this is a standard z-score at 1 minus alpha. Here I've chosen alpha of 0.5 divided by the square root of n. And here it's just minus that quantity. So the idea, excuse me, is when you plot these, any bar or correlation that ends up outside of this interval, like down in this space or up in this space, would deem significant in a null hypothesis testing framework. Another interesting thing about this is, again, this is what standard R output will look like. But if you think about this, this confidence interval should not be flat for all lags. It should actually increase as the lags go out because the sample size here is actually getting smaller, right? We've taken a time series, we've replicated, now we're shifting. We started with a time series that was 20, and then now we're comparing 18, 19, 18, 17. So the denominator here is getting smaller, which means this value is getting bigger. So in theory, this should look a bit like a cone on its side where the confidence interval is getting wider as it goes out. But standard would dictate this technology. And again, when n is really large, it doesn't make much of a difference. If n is 20, it's going to be appreciable. If n is 100, 200, something like that, you would hardly notice. In R, it's really easy to get the autocorrelation function. It's just ACF. And then remember on Tuesday, we talked about time series objects. Well, this is one way to do it. You could also just pass it a regular vector. It doesn't care. And when you do that, by default, it will generate a plot that looks like that. So let's look at the autocorrelation function for some deterministic forms of models now, because this will help us when we start looking at stochastic models where there's actually some wiggle in them. So here's just a time series that's a linear trend. So at time 1, it's 1, at time 2, it's 2, etc., all up to at time 100, it's 100. And here's the autocorrelation function. So right, it equals 1 at lag 0, and then it's going down like this. So this autocorrelation function for a linear trend looks pretty linear, and it's declining. Here's a discrete sine wave. So right, this is the one that goes up and down, wiggles up and down, wiggles up and down. And this is what I had said before, that the ACF for a periodic function is itself periodic. Because at some point they're in phase, and then slowly they get completely out of phase. So here they're really highly positively correlated. Then at some point you'd get its monthly data. So at lag 6, we're looking at January and July here now. So they're completely out of phase. And then you get them lined back up, and then by the time you're at a 12-month lag, you're back to January and January's. So when you look at something like this, if I hadn't showed you the panel on the left, just the panel on the right, you should be able to identify this as being, oh, this is indicative of some sort of periodic signal in the time series. How about a linear trend plus a seasonal effect? Well, what you see here is there's still this kind of strong periodic signal, but it's being damped. So these peaks are slowly getting lower. And ultimately these would collapse, and these are actually starting to grow. So you've got this kind of thing that's running down like this, but it's going like this the whole way. Here's a sequence of 10 random numbers repeated 10 times. So this is kind of useless, it's meaningless. This shows that every once in a while you get these strong positive significant things, strong negative positive. So looking at something like this, it's just like, you wouldn't be able to look at this and immediately say that's what this looks like. But it would suggest that you've got some repeating pattern here, just based on the way these are. You have high, low, 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 high, 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 low, low, right? So something like that. Okay. So that's autocorrelation. And if you think about autocorrelation, let's go way back to elementary school here and think about the transitive property of mathematics, right? And that says that if A equals B and B equals C, then we know that A equals C, right? That's pretty straightforward. That would suggest to us that if X is proportional or correlated with Y, and Y is proportional or correlated to Z, then there's a pretty good chance that X and Z are also correlated to some extent. So this would suggest then that X at T is proportional X at T plus 1, X at T plus 1 is proportional X at T, and therefore X at T is proportional X at T plus 2, right? Just because we've induced this sort of correlation by the fact that they were next to one another. So here's one, here's another. These two are going to look like each other because there's one in between them that's also correlated with them. So this motivates what's called the partial autocorrelation function. And the partial autocorrelation function simply measures the correlation between a time series and a lagged version of itself, X at T plus K, with the linear dependence of the intervening series all removed. So the idea here would be, we know X is roughly equal to Y, Y is roughly equal to Z. We want to know how proportional X and Z are. Well, we're going to remove this dependency and only evaluate this. And you can do this by hand if you're really glutton for punishment, or you can just ask R to do it. But the idea here is that you essentially have to estimate a regression model on all of the backward lagged variables, another one which is on the forward lagged variables, and subtract those out from your observations, and that gives you this partial autocorrelation function. So that says we've got this time series, we replicate it, we're going to shift it and look to see where the partial autocorrelation between this point right where my fingernails are, basically. But we want to get rid of all the rest of my finger in here. We just want fingernails, none of this other bony stuff. Okay, so here's a real world example. This is abundance of Cryptomonas, which is a small phytoplankton from Lake Washington, for roughly monthly samples for about almost 20 years, 18 years, something like that. Here's the autocorrelation function for those data. At lag 0, it's 1. And at lag point, what's going on here? Well, this is R being a little bit weird. And the issue here is that for some reason, if you have monthly time series object, you've set this up as a TS object. And you said it starts on 1977 month 1, and it goes to 1995 month 12. R is like, aha, that's a monthly time series. So when you then look at lags here, the lag for whatever reason is being pinned to the year, not to the month. So this is 1 year here. This is 6 months here. It's fractions of a year. So this is something to just be aware of when it's, and as far as I know, it's only monthly data that ever does this. But this can be really confusing, right? Because there's no such thing as fractional lags. Lags have to be an integer value. So just be aware of that. But this says at 1 month away, there's still pretty high correlation. 2 months away, yes. 3, 4, not so much. Maybe 5, 6, yes. And then of course, a year later, they look like it again. So this means, right, Januaries look like Januaries. Yes, so did everyone see Eli's point there in the chat? If you had a vector of values, and you hadn't created a time series object from them, and you just stuck those into ACF, it would call this 1, 2, 3, 4, etc. This would be a 12, that sort of thing. Okay, and here's the partial autocorrelation function for that. And importantly, in R, it has now dropped lag 0. Remember where the correlation was 1 before? So this is now the first lag, second, third, fourth, fifth, sixth, seventh, etc. So you hear autocorrelation, partial autocorrelation. So we've lost several of these otherwise correlated values, right? So here, because this says, oh yeah, a year later, they're still really highly autocorrelated. But from a partial standpoint, not so much at a year. Once we get rid of the fact that, you know, January is related to February, February is related to March, et cetera, et cetera. So we start to lose that structure once we get rid of all the intervening correlations. Okay, on Tuesday next week, we're going to see that the ACF and the PACF are very useful tools for identifying orders of ARMA models. And that will make a lot of sense to you 5 days from now. Okay, so now we have autocovariance, we know something about autocorrelation. Now we typically often are want to look at the association not between one value in itself, but two different things, X and Y, just like when we talked about covariance. So here we can just extend that notion of covariance to cross covariance. And to do so, from a sample, here we're going to take X at t minus the mean, then we're going to take Y at t plus some lag. And again, this could be minus the mean of the Y's. Sum those up, divide by the sample size, and you get the cross covariance function, I'm sorry. Now, based on that, we can again define a cross correlation function, just like we did a correlation function, right? So here all we have to do is take the cross covariance function and divide by the standard deviation of X and the standard deviation of Y, and you get the cross correlation function of X and Y at some lag K. And just as with any of those other measures of correlation, this is going to be bounded between -1 and 1. Okay. So something that's really important to point out is that estimating the cross correlation function in R is a bit tricky. It's really straightforward, and that's just this function CCF, and then you pass it your X and your Y. But if you look into the help function for this, you have to figure out what the lag is it's talking about. Sorry, there's somebody vacuuming outside the door right now. The lag K for this function is really the correlation between X at t plus K and Y at t. And so in an explanatory context, right, for a lot of us who are thinking about, maybe we're imagining that Y is a function of X, right? Like this is, maybe Y here is fish growth and X is temperature. We really want to think of, Y as a function of X, so it's helpful to use Y, CCF, and then pass Y comma X, and rather than X comma Y, and only consider positive lags. Because it's funny that way, but what this would suggest is that now X never leads Y, Y always leads X. And it's really confusing. I have to check this help function in R all the time or I screw this up. So if you're comparing two time series with cross correlation, I recommend you do Y and X and then only look at positive lags. Okay, so here's an example of cross correlation. You saw this time series plot the other day. This is the number of lynx trapped in Canada from early 1800s, the early 1900s. Here's sunspot activity. And here I'm thinking that sunspot activity leads links. Okay, so what I'm suggesting is that we should only consider positive lags here. And by default, R will return minus lags to positive lags, unlike the ACF and PACF functions. So at time 0, doesn't look like there's any correlation between these two. But after you get out 4 months, it looks like there's a negative correlation between those. So 4 years, I'm sorry, not months, 4 years. So 4 years after you have high sunspot activity, you have low links numbers. That's what that suggests. 9 months after you have, years after you have high sunspot activity, you have high numbers of links. And like I said, it's hard for me to think about this by considering the negative lags, because it doesn't really make sense for me that links is influencing sunspot activity. Oh, sorry. Yes. So Logan, do you see Amelia's comment there? Oh, no, sorry. It's CCF links, comma, sunspot. Yeah. So this is my Y, if you will, and this is my X. So I'm doing, yeah, CCF links, comma, sunspot. Okay. Any questions on that before we move on to considering some simple time series models?
I have a question, Mark.
Yep.
You're always starting at like, it's with respect to time, you're comparing it to like t equals 0 or something? Or I'm thinking more about the ACF plots we were seeing before. Like, do you make multiple of those plots for different, like starting at different time points? Or would it look the same, or?
Yep, no, so that's, yeah, good question, Jessica. So no, you don't have to do that. So this says, take a time series, replicate it. What's the correlation right now? It's 1, because it's just the exact replicate of one another. If you shift this a little bit, now they're not the same anymore, but January is kind of like February, that sort of thing. You shift it again, now you're asking, is January like March? Shift it one more time, is January like April? That sort of thing. So no, you only ever have to do one of these. And here would just be, January, February, January, March, January, right? That sort of idea. Yep.
Okay, thanks.
Any other question? Okay, and we're going to see these again on Tuesday when we talk about ARMA models too. Okay, so let's talk about some simple time series models. A time series, we're going to call it now WT, is discrete white noise if its values are independent and identically distributed with a mean of 0. So IID is what you often hear about, right? And we talked, those of you who took Quorum 514 with me last spring, we beat this into the ground pretty hard, right? So the idea is that we want, it doesn't matter here if we, so think about what this means. Independent, that means at any lag, there should be no autocorrelation. And there shouldn't be any change in the variance or the mean. Right? We shouldn't have anything that looks like this bizarre conical shape, or it shouldn't be trending up, or it shouldn't look like a parabola, these sort of things. Okay, so here's an example where I'm going to change some of these things because the distributional form for WT here doesn't really matter. I just said it's discrete white noise if they're independent and they're identically distributed with a mean of 0. So here's a time series model where I said WT equals 2 times E of t minus 1. And E of t is drawn from a Bernoulli distribution with a probability of 1/2. So as a refresher, a Bernoulli distribution can only take values of 0 and 1 with this probability. So this is a description of a coin toss right here. So if this is 0 or 1, if it's 0, this is 2 times 0, this is -1. And if it's 1, this is 1. So this time series is just vacillating between -1 and 1. And sometimes you get the same value for multiple times and that sort of thing. And if you look at the autocorrelation function for a white noise series, the correlation's 1 at 0, that's good, but it's not significant anywhere else, right? So this is our notion of independence here. No temporal dependence whatsoever. Okay, that's a bit of an odd example. Very rarely would you see a time series model like this, but it could happen. Most often we think of white noise as being Gaussian, and certainly in this class, that's what we'll consider exclusively. So in that case, we could write a Gaussian white noise series where our value at time t is drawn from a normal distribution with a mean 0 and some variance. Given this, the autocovariance at lag k will equal the variance if it's 0. We talked about that earlier. And it's going to be 0 if k is greater than or equal to 1. The autocorrelation at some lag k is going to be 1 if it's lag 0, and it will be 0 for any lag greater than 1. So these are properties of Gaussian white noise. Okay, so here's a simulated time series, 100 length long, of Gaussian white noise. So and it's a standard normal. So it's got a mean of 0 and a variance of 1. And now I've plotted the autocorrelation function next to it. And you can see here at lag 0, it's 1. That's true. And everywhere else, it's non-significant except this one. Oops, I just told you that this should be essentially 0 everywhere. So does anyone have a guess as to what's going on here?
Is it because if your confidence interval is like 95%, you'd expect some like 5% to fall outside that bounds?
Yep, that's exactly right, Jessica. Yeah, so right, we basically conducted 20 null hypothesis tests, and by chance alone, one of those is going to be significant. So this is something else you kind of have to keep in the back of your mind, where sometimes people look at autocorrelation. I see this a lot more commonly with cross correlation, where somebody will be looking for a relationship between two variables and they've shifted them and they're like, oh man, I got this significance at 7 months out. And you start asking them, well, what's the ecological significance of that? Well, there is none, but it's really interesting. And then I say, that's probably a statistical artifact. Try it again. So it's just something, again, kind of put on a sticky note, put on the corner of your monitor somewhere, and just remember that even though theoretically this should essentially be 0 everywhere, it's not always the case. And so any of you, if you have an R window open, simulate one of these, but make T like 10,000, not 100, and compute the ACF on that. And all of these will be barely visible in here. I don't think you'll get any of them are significant. So it's a sample size game. Yep. Okay, another model which we saw just briefly on Tuesday are random walk models. And these are really important in time series analysis. They're super simple, but they actually are rather flexible. So they allow you to fit lots of different kind of patterns, even some that you would think would have way more structure than this. And we say a time series is a random walk if the value today equals the value yesterday plus some white noise. That's it, it's that simple. If we're talking about random walks now, the mean, the expectation for that is 0. But now the covariance or the autocovariance is a function of time here. So it's your background variance, sigma squared, but it's times t here. And similarly, the autocorrelation is now going to be a function of time. So t shows up in this formula as well. So let's see what that looks like. So because this is a function of time and this is a function of time, random walks are not stationary. We will probably say that every day from here on out. If there was a final in this class, that would be the first question. True or false? Random walks are stationary. No, 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 never. Okay, here is a simulated random walk, just like this, with white noise. So I just took a standard normal deviates, basically added those up. Here's what it is. Here's the ACF for that. So now, unlike white noise, right, we get significant autocorrelation at lots of lags. I mean, shoot, out to lag 13 in this example, they're all highly correlated. So this is sort of what I was referring to earlier when I talked about a smooth series compared to that, which is choppy. So choppy time series have small autocovariance and autocorrelation functions for large lags. Smooth series have large autocovariance and autocorrelation out to large lags. Okay. Any questions on white noise or simple random walk models before we go on? Yes, thank you, Eli. So time here is lag. So it's, you see what she's got typed in the text there? Oh my God, somebody. And we'll see more of this as we move forward as well. Okay, so let's talk about a couple of time series operators. And again, we won't use these much at all moving forward. You're going to see one of them in particular on Tuesday, but it's something that you'll almost certainly see when you start reading textbooks or even some papers related to time series analysis as well. The first one is what's called the backshift operator. And we usually write this with a bold capital B. And really all that is just what it says. It just says shift something backwards. So if we take B times x of t, that's really all that is just say, well, just shift this backwards one time step. So bx of t just equals x at t minus 1. Or more generally, you might see this as b to the k, because this could be, if this were b to the 2 times x at t, this would be x at t minus 2. So it just says shift this thing backwards some number of steps. So here's a random walk model. X of t equals x at t minus 1 plus some white noise. And we could write that with a backshift operator. So we could just write x at t, and now instead of x at t minus 1, we have b times xt. We can move this over to the other side, pull the 1 minus b out, and then divide that out. And here now we have x of t equals essentially wt over the quantity 1 minus b. This model up here at the top and this model here at the bottom are entirely equivalent. This one, at least to me, is much easier to read and understand. But nevertheless, you are going to see things like this in the literature. And just something to be aware of. And this backshift operator we're going to see again on Tuesday, because it will help us in identifying some important aspects of time series. Okay, the next operator that's important, and this one we'll actually probably use a little bit toward as class moves on, is what's called the difference operator. It looks like usually it's written with this gradient symbol. And so the difference of xt is just equal to x at t minus x at t minus 1. So you can think of this as sort of the derivative. It's the change in a time series from one step to the other. So if you first difference a random walk, you get white noise. Okay, so if we first differenced this, there really should be a parenthesis around here. So this says, okay, first difference this, that says x at t minus x at t minus 1. Got to do that on both sides. This one and this one cancel out. No, I'm sorry, this one and this one cancel out. So that would say x at t minus x at t minus 1 is white noise. So if you take a time series, a random walk, and you first difference it, you'll get white noise. The flip side of that is if you had a white noise series and you essentially integrated that by one time step, you'd get a random walk. And we can show you a pretty slick example of that in lab. It turns out that these two operators are actually related to one another. So the difference operator raised to some power k is equal to 1 minus the backshift operator to some power k. And this is really much more like gee whiz stuff here. I don't think anybody's really going to have to file this away because you could just Google this and figure, you know, I don't suggest you commit this to memory unless you're really, really eager to do so. So for example, if we took the difference of x at t, that's x at t minus 1. And if we had 1 minus b to the x of t, well, just multiply that in. That's x of t minus bx of t, and we know that this is x of t minus 1. So those two are equivalent. So one of the interesting and important bets of differencing is that we can use this to get rid of trends in data. So remember we talked about if a time series has a trend, it's not stationary. And we may be interested in only examining stationary time series. So if we differenced it, we might now be dealing with a stationary time series. It's a bit different. It's sort of a derived product, right? It's sort of the derivative, but that could be it. So first differencing would remove a linear trend. Doing this twice, so difference it once and then difference it again, would remove a quadratic trend. So right here on the top is essentially a biased random walk here. So it's this thing that's wiggling, but it generally has a positive linear trend here. And if we first difference that, you'll see here, there's no trend in these data at all. But you'll also see that this time series was 50 units long. This one is now only 49 units long, right? Because we lost one of those when we took the difference. You could also remove seasonality with the difference operator. So using a first difference with k equal to the period in the data will remove both a trend and seasonal effects. I'll show you an example of that. So here is temperature data from Lake Washington. It's cold in the winter, warm in the summer. Here's the first difference of that time series here, right? So there's still some structure in this time series. It still actually has some fairly strong autocorrelation in it, but you don't see any of that seasonal signal here in these data. So this was a case where basically January's get subtracted from January, February from February, et cetera, right? So you've got rid of, so you can imagine there's some kind of typical sign period in here that we talked about on Tuesday with respect to the classical decomposition. We got rid of that, and here's what's left. So differencing in this case, and essentially we lost a whole year of data now, so I probably should have scaled these. See, they both end right here, but this one starts much later now than this, because we had to do a difference of a whole year. So we actually threw out 12 months of, well, we didn't throw out, but right, we're looking at the change from January to January, the change from February to February, that sort of thing. In R, there's a function to do this for you. So you don't actually have to line the two things up and then subtract them. And it's called diff, very cleverly. And it has basically 3 arguments: the data, the vector itself, the lag at which you would like to difference it, and the number of differences you want it to do. Okay, so lag is going to specify t and it's minus h's now. So you're only considering negative lags. The default is 1. So this is something you would use for like non-seasonal data, like that random walk that I showed that had a linear trend. We just did a difference at lag 1, and it took care of that. If you had quarterly data, you could set that to 4. If you had monthly data, you'd set that to 12. Differences here is the number of differencing operations you'd like this to do. So you could pass diff on an object and then embed that in another diff call. If you just had differences set at 1, that'd be the same thing as if you just called it once and set diff equal to 2. So if you had diff equal to 3, you could get rid of a sort of polynomial, third order polynomial, right? Okay, so today we learned about some characteristics of time series, these sort of statistical properties. You learned how to compute the autocovariance and autocorrelation and look at those via correlogram. You even saw the partial autocorrelation function. We saw something about white noise and random walks, and we've seen the backshift and difference operators. So any questions on any of that stuff?
I have a quick question. Well, hopefully it's quick. So we had 2 examples. We had like the random walk and the Gaussian white noise. And we plotted the time series, and you said that one was choppy and one was smooth. And in my head, it didn't make sense why one was choppy. Like the one that you said was smooth looks choppy in my head. So I'm wondering how to make that clear in my mind.
Yep. So yeah, Brielle, that's a really good question. Let's go back here. Okay. Here was, do we agree that this one looks pretty choppy? It's kind of, right, it's that fuzzy caterpillar on a, right? That's kind of characteristic of white noise that definitely has this high frequency variation. This random walk, when I say it's smoother, yes, this is jitter. It's not, like a really straight line. But if you just sort of look, there's obviously some structure here, right? This was kind of high, then it clearly went down, and then it started drifting back up, that sort of thing. So that's what I mean about smoother. And some of it depends on what you use for this variance. Like if you'd set this variance here at 0.1, so it's actually standard deviations in R, but anyway, if this was 0.1 instead of 1, this would look a lot smoother, so to speak. But based on the scale, oops, this one would still look pretty choppy.
Thanks.
Okay, so Eli has pasted a couple of examples into the chat that you can take a look at. And we can do this in lab here too when we move over there. We can just show you some quick and easy examples. So let me just quickly, oh, sorry, before I do, does that seem, is that okay, Brielle? I mean, I think it's, after you look at these things enough, you'll start to see, like, by the end of this course, you will be able to look at a time series that is a random walk and you'll be, gosh, that looks a lot like a random walk. It's kind of this, got this, yeah, it chops, but it tends to do these smooth things. Fun fact about a random walk, if you if we simulated this over infinite time, a random walk in one space will visit all of these points with probability 1. And in 2 space, it will not. And in 3 space, it never will as well. So this is something that you can pull out at a cocktail party. We can all get together sometime. But wait until later in the evening after everyone's had several drinks. Okay, other questions?
I have a question going back a little bit. For the TS object, if you had daily data, would your frequency just be 365? Is that how it'd be used in that way? Or
just one? You would treat it like, well, do you have multiple years of daily
Right,
data?
or just 1 year, right.
Yeah, if
Okay.
you only had 4 months of daily data, then it would be 1. But yeah, if you
Okay.
had many years of daily data, then you could use 365.
And hope there's no leap years, I guess. Yeah.
Yeah,
Okay.
that's-
Okay. Cool.
I've never seen anyone use 365 though.
yeah.
Okay.
It's usually just quarterly, daily, you know, sometimes hourly, 24-hour.
Yeah. Yeah, and the truth of the matter too, Amelia, is that in a lot of these situations, the time series object you don't even need from an analysis standpoint. Like you'll see when we start fitting state space models, using different, we won't even bother with time series objects. We'll just be looking at vectors or matrices. Yeah, but there's just, and there are some new additional packages in R. There's the XTS package, which is another one that has its own object, which for time series things. There's one in the tidyverse now, I'm totally blanking it. There's one that you can use for, somebody help me out. I'll figure that one out. But there's another one that will do it where it handles time objects really well. But the bottom line is, yeah, I mean, for a lot of the tools we'll use, the time series object is not at all important.
Yeah, the time series object, the main thing it's doing is keeping track of the time and keeping track of like if there is any frequency in the data, like if it is quarterly data. And that's going to be helpful when like you're plotting, for example, and it would be helpful too when you're fitting certain types of models if you use that. So I can back up a little. If the function that you're using uses that frequency information, but there's nothing like I don't know, like super special about the time series object. It just has that information about time in it. So like it has the information that your data are starting in 1970 on day 10, for example. That's one of the things it would have. So then when you plot, it would automatically could show the year and month or something.
Yep. So yes, Rachel dredged up, it's Lubridate is the package that I was thinking of. That's one for working with actual dates and time objects. Other questions? Oh, okay, let me jump over here for just a second because I wanted to show you. Oh, that's from here. Sorry. Oh, in the lab book. If you go to chapter 3, you'll see a bunch of the stuff we talked about on Tuesday. And then here in chapter 4 is some of the stuff we've covered up early. And then by the time you get down into here, this is stuff we'll talk about on next Tuesday. But right, if you want to learn about TS objects and plot TS, this is some of the stuff we talked about. So here I basically have recreated there's the Mauna Loa time series. We talked about decomposition the other day. And we're going to skip over some of this in lab just because you can all go back and do it. This is actually worth doing because if you if you follow through this, we'll show this is the example we used in class. We took this, we have to figure out how we're going to do the objects. First thing, right, was to estimate a linear filter. We used a moving average. So here's a 12-month moving average for the Mauna Loa data. Okay, so we get this out. There's a filter function in R you can use to do this. That's what's left over. There's the trend. So then I was saying, well, once you have the trend, you just subtract that from X and you get your seasonal effect. That's what this is here, except that's still got the error problems in it. So then basically you had to go through and compute all of the monthly means, subtract those out so that then you get this, here's the seasonal effect. And I'm sorry, I'm going a little bit fast, but you all can go back and dig through this. And then you would just essentially repeat this 12-month series here as many years as you had. So then once you had your estimated trend, your estimated seasonal effect, you'd subtract that and get the errors. So this is essentially what this is. So here's the original data series. There's the trend. There's the seasonal component, and there's the leftover noise. So for those of you watching at home, that was quite a bit of code when in fact, all I could have done was just say decompose CO2 and it would have done all of that for me. But it's good to actually see how it's done. But if you follow along and do these steps and do it the long way and then do it via decompose, you will get the exact same answer. Yeah, and then up here too, we had some this is stuff that you saw with respect to Tuesday's stuff as well. So there's some information here in our lab book that's mirroring what's going on in lecture, and I just wanted to make sure that everybody's aware of that. So you can go back and see that as well. Okay, that's all I had for the quote lecture portion of this course.